Hello everyone, and welcome to the Big O Examples lecture. So what we're going to be doing here is showing you various examples of Big O notation and what those algorithms and functions will look like. So at the end of this, there's a reading assignment. So here I have open the Jupyter Notebook, and if I scroll down here, you'll see there's a homework assignment. So make sure that after we go over this video, and once you've gone through this Jupyter Notebook, you check out these two sources, which are additional explanations of Big O notation and various Big O examples. They're great explanations, so go ahead and check them out. Okay, so let's go ahead and start off with our own examples. So what we're going to do is start with some simple examples of various Big O functions. So the first one we're going to explore is the constant, so O1. So I'm going to make a function here, and I'm going to call it func_constant, and it's going to take in a list of values. And what it's going to do, it's going to print the first item in a list of values. So it takes in a list called values, and it says print values, takes that first index, and let's go ahead and run this. So if I say func constant, remember, I'm just doing tab for autocomplete. I can then go ahead and pass in a list. Let's go ahead and just say LST and assign LST to be the list 1, 2, 3. Okay, so I've run that cell, and let's see what happens here. I get a result of, let's zoom in, of 1 here. And if you notice, I'll always get that result no matter how large that list is. So this function is constant because regardless of the list size, the function is only ever going to take one constant step size, in this case 1. So it's just printing the first value from a list. So we can see here that an input list of 100 values will still just print one item. Even if it has 10,000 values, it's still going to print one item. So a list of n values will still just print one item, which is why this is of constant Big O. So let's move on to linear. So we'll make a function here called func_lin. It'll take in a list object. We'll just call it LST in this case. And this will take in a list and print out all the values. So it's going to say for val in LST, print val. And if we go ahead and call that on that list we just made, note how we get every single value printed. So this function runs in ON, or linear time. So this means that the number of operations that are going to take place here, the number of print statements, is going to scale linearly with n. So if we have an input list of 100 values, it's going to print 100 times. If we have a list of 10,000 values, it's going to print 10,000 times. And a list of n values will print n times. So that's why this is a linear example. All right, finally, let's go ahead and check out a quadratic example. So let's say func_quad, and we'll have it take in LST, and it's going to print pairs for every item in a list. And what I mean by that, it's going to say for item 1 in that list, and then for item 2 in that list, go ahead and print item_1, item_2. Okay, so let's go ahead and see what this looks like. I'm going to reassign the list to just be 1, 2, 3, and then I'm going to call that function on that list. And let's see what we get here. All right, so what happened? So note how we have two loops, one nested inside the other. This means that for a list of n items, we will have to perform n operations for every item in that list. So that means in total, we will perform n times n actions here. We're going to print this n times n times. So that's going to be n times n, or n to the power of 2, n squared, which is quadratic. So a list of 10 items is going to have 10 to the power of 2, or 100 operations there. So you can see how dangerous this can be for very large inputs, and that's why big O is so important to be aware of and is such a crucial part of the interview process. So now we're going to move on to a section of calculating the scale of big O. So we want to discuss now how insignificant terms will drop out of big O notation. When it comes to big O notation, we only care about the most significant terms. So remember, as the input grows larger, only the fastest growing terms will matter. And if you've taken a calculus class before, this is going to remind you of taking limits towards infinity. So let's go ahead and see a quick example of how to drop constants. I'm going to make a function called print underscore once. Takes in a list, LST, and it prints all the items just once. So it's going to say for val in LST, print val. And now if I call print once on that list, I just get 1, 2, 3. So what is the big O of this function? Go ahead and take a moment to think about it. All right, hopefully you saw that it's just on, it's linear. You're going to do an action n times for the size of the list. Now I'm going to show you a different example. I'm going to call this function print underscore 2. And I'm going to say for val in LST, print val. And then I'm going to do it again. I'm going to say for val in LST, print val. So now let's call this function print underscore 2. You notice I get an output 1, 2, 3, 1, 2, 3. So now the question here is, what is the big O or performance of this print underscore 2 function? Notice we are printing it twice, but what's actually happening here? It's not going to be n squared because it's still linear. It's going to be n plus n, so 2 times n. And this is where we get to terms with insignificant or significant constants. So we can see here that the first function we made will print on the order of on, and the second one will print on the order of 2 times n. So it's going to do it twice. However, if n is going to infinity, the constant can be dropped, and that's an important thing to remember. You're going to be dropping most constants and only focusing on the terms that grow the fastest and have the largest effect. So in this case, both of these are order n. They're big O(n). So this is O of n, and this is also O of n. Now, as I mentioned before, in reality it's really just 2 times n, but we're going to drop the constants there since 2 times infinity is going to basically be the same as infinity. Okay, so let's go ahead and see a more complex example of this, of dropping these insignificant terms and these insignificant constants. I'm going to make a function called comp, and it's going to be 3 parts to it. What it's first going to do, it's going to print the first item in the list. Once it's done with that, it's going to print the first half of the list. So the way I'm going to do that is I'm going to say, going to call a midpoint equal to the length of that list divided by 2, and then I'm going to say for val in list, and I'm going to slice it all the way to the midpoint index. I'm going to say print val, and then I'm going to say for x in range 10, this is going to be the third operation. It's going to print a string 10 times. It's going to say print, let's just say hello world. Okay, so let's go ahead and make a list. I'm going to say 1, 2, 3, 4, 5, and then call or pass that list into the function. And I get 1, 1, 2, and then hello world, hello world, hello world. Let's go ahead and make this list a little larger so the effect of that midpoint is a little more obvious. All right, so 1 and then 1, 2, 3, 4, 5. and then 10 hello worlds. So what is the big O of this function and the algorithm within it? So let's break down the operations here. Well, notice the first operation, this prints the first item, is O1. So I'll comment that in here, O1. Okay. Now what about this middle operation, which I'm separating with some comments here? So if you notice here, we're going to go all the way to n divided by 2. So in this case, this is order of 1/2 times n, which is the same as n divided by 2. Now keep in mind that this is the same as order of basically 1/2 times n. So just keep that in mind. This is still a constant. So n divided by 2 is the same as 1/2 times n. And that's going to be important because we're going to keep the idea that as n gets larger, these constants will go away. And then this last one, it performs the action 10 times. So it's a constant. So it's going to be constant officially 10 there, order 10. So first part, order 1. Second part is order 1/2 times n. And third part is order 10. So in total, what we can do is add all of these up. And you may need to do this in an interview setting, is add up the different components in order to figure out the entire big O. And in this case, we get something that looks like this. We have an order, or big O, and let's go ahead and make this a markdown cell. So right now, that's the order of that function. 1 plus n divided by 2 plus 10. But now we can actually simplify this. We can see that as n grows arbitrarily large, remember that was part of our definition of big O. As n grows larger and larger, this 1 term and this 10 term become insignificant. And then this 1/2, or the divided by 2 term, multiplied against n, as it grows larger and towards infinity, is really not going to have much an effect. So that means that this function is actually can be simplified down to be of order, or big O, n. All right, so let's just do a brief overview of what we did there. In order to figure out the big O of this entire complicated, well, semi-complicated equation or function, we separate it out into parts, right? Then we put them all together, and then we simplified it as n grows arbitrarily large. And then finally, what I want to discuss is worst case versus best case. So many times we are only concerned with the worst possible case of an algorithm. But in an interview setting, it's important to keep in mind that the worst case and best case scenarios may be completely different for different big O times. So let's see an example and consider the following function. I'm going to make a function called matcher. It takes in a list and it takes in some item you want to match. And what it does is, given a list, it returns a Boolean indicating if a match item is in the list. So I'm going to say for item in list, if item is equal to match, return true. If no true is returned, then the function will return false. Okay. So remember, I have my list here. It's 1 through 10. And if I call matcher on it and pass in a list and then say I want 1, it's going to return true. So 1 is in that list and we got a match. Now if I call matcher list and I say a number that's not in that list, such as 11, notice I get a false here. Now, when we're concerned about big O, you notice that we have a best case here. So the best case is that the match occurs in the first item of that list. And that means that in this particular best case, you actually have a constant runtime here. The best case is actually O1, constant, since the match is found at the first element. In the case where there is no match, every single element has to be checked, which is going to be n elements. So the worst case is ON. Now, in an interview setting, you're pretty much always dealing with either worst case or sometimes average case. And we'll discuss that in further detail for different data structures. But you can consider it, if someone's asking you what is the big O, consider the worst case. But make sure that you make a point of considering best cases as well. Now finally, I'm going to introduce the topic of space complexity. Many times you're also concerned of how much memory or space an algorithm uses. So right now we've been talking about performance or time complexity, but we also want to keep in mind space complexity. And I'm going to show this through just two simple examples. So I'm going to make a function here called def create list. It's going to take in n. And what I'm going to have here is make a variable called new list, which is just an empty list. And then say for num in range n, new underscore list, append a string called new, and then just return new list. Okay, so if I say create list 5, here I have 1, 2, 3, 4, 5 news there. So note how the size of the new list object, this object, scales with the input of n. So right now I'm just talking about space or memory. So in this case, this shows that it's a big O of just n, or linear, in regards of space complexity. It'll have to take up n items in memory. All right. So another example I want to show you is a function I'll call printer. And it's going to print hello world a number of times. So it's going to say for x in range 10, go ahead and print hello world. So if I call printer and I pass in 10, it prints hello world 10 times. So what's the big O for the time complexity here? Well, it has to do this n times, so it has an ON for time complexity. So for time complexity, this is linear. But what about space complexity? How much does this algorithm actually have to attribute to memory? If you notice, it's printing the same thing over and over again. It doesn't actually have to save n items. It just has to save one, the hello world string. So as far as space complexity, it's constant. It has O1. So that's an important difference to make here. In this case, we have space complexity is a constant, O1, since we're only having to save in memory this one item, this print hello world string. But we're doing it as far as time complexity, order n. Okay, so that's just something to keep in mind, that there may be trade-offs between time complexity and space complexity. Usually in interviews, you'll be concerned with time complexity, but depending on the interview question or case or who your interviewer is, you may be asked about both space and time complexity. So it's important to keep them both in mind and know the various trade-offs in certain situations. All right, so as I mentioned before, at the end of this lecture, there's a homework assignment. So make sure you go ahead and read those two explanations on more big O notations and more big O examples. All right, just to review what we did here, we went over various examples of different big O notations and big O common functions. All right, thank you very much, and I will see you at the next lecture.